Yeah, good morning. Thank you very much for the introduction, Nicola. So I will talk about today about how we use machine learning in order to decarbonize the building stock. I will give you two examples, whereby one of these examples, Emmanouil, a PhD student in our lab, will introduce more in detail because he has actually done that study and he knows much more about it. So as a starting point, why are buildings important? If you look at the total energy consumption of a country, this is, for example, for Switzerland, we see that alone 40% of this energy consumption is due to buildings. And we see here also that most of this, or the problem with buildings' energy consumption is that it's usually covered by fossil fuels. So, for example, in Switzerland, it's mainly oil and gas heating systems which are in place. So if we want to decarbonize it, the only solution what we can have is basically that we replace these fossil fuels by renewable energy technologies. Let me start by the CO2 emissions. So what role the CO2 emissions play, that's quite a famous equation which was already used by IPCC, which shows the effects of certain factors on the total CO2 emissions. And the overall goal is what we have to actually bring that CO2 down to zero, which means one of these factors has to come down to zero. Let us go through these factors quickly. So we have the people on the planet. We have the services, what these people consume. Then we have the energy, what goes into these services. And the last one is that actually how do we cover these services? So what energy do we use? So basically the CO2 emissions. The first one, we quite clearly see that there is no possibility that we actually can reduce that. So the only option what we have is actually that we can reduce our energy consumption and that we reduce the CO2 emissions by replacing fossil fuels through renewable technologies. We can also use that same equation and apply that to the building stock, what would mean basically that we have to make our buildings more energy efficient. So we have to reduce the energy per square meter, for example, and we have to replace then the fossil fuels. So basically the CO2 emissions per energy what these buildings consume should go down. What is the problem with renewables? If we look at them, here's an example for a day and a year. In red, the consumption. In yellow and blue are the production or potentials, basically. So PV on the left side for a day, and then on the right side, you see PV and hydropower. What we clearly see here is that actually the demand and the supply doesn't match. So we have to find solutions how we can shift that energy consumption to the times when actually the production is taking place. Or the other way around, we have to find ways how we can store that energy and on the short term and on the long term and actually shift that production to that periods where we actually have it. So we work on basically on different modeling techniques in order to address that. So we need to know quite clearly what is the demand of buildings, what is the potential of renewables at a very high time resolution and geographical solution. And then in the middle, we work on different modeling techniques to address, basically to make an energy balance or to manage the energy flows. And on the right side is then you see the operation. So actually, how do you then operate an energy system where you have a lot of renewable energy technologies installed? So if we go back to our buildings and we want to address these different things, what do we need? We need a lot of data. One is that we need to know what is the energy consumption of buildings. So this can be either through measured data in very high resolution or simulated data if we don't have this measured data. We need to know a lot on the existing situation. So what is the 3D or 2D building information? There are a lot of statistics which we can use about heating systems, building renovation, statistics on how people actually behave, and then also geographical information systems on grid regions, heating demand atlas, and so on. And we need to know also the renewable potentials, ground source heat pump potentials, PV, biomass potential, and so on. The problem here is usually that actually this measured data are usually not, at least not in a very high time resolution available. So that we need actually to develop then models how we can overcome this. And there is then also where machine learning comes into play. So I show you a number of examples where we use machine learning techniques. So one is, for example, if you do a building or district scale analysis, to handle these different data sets, you need clustering or classification methods in order to handle the large amount of data. Another one is that if we want to retrofit buildings and we want to do that at a large scale, so upscale that to the whole country, for example, we have to handle a lot of data also here. So we also use, in this case, neural networks, for example. Or if you go to the developing countries, you have even less data available. So we use, for example, regression models to overcome or to predict energy consumption. And the last thing is then on the operational side. So we have a demonstrator at our Empa campus where we collect a lot of data. So it's actually a vertical district where we can measure the operation, and we use then different techniques to do demand forecasting and to optimally control these buildings. We will show you now two examples, so the middle two ones, where Emmanouil will then talk about this retrofitting, and I will then say something about these developing countries. Starting now with the first one, upscaling of building retrofit for residential building. So if we would take an engineering-based approach, we use data. We have a building simulation tool which we automated at the urban scale in order to predict the energy consumption, the very high time resolution. And we can then predict basically the energy consumption and then also do different retrofitting scenarios. So how is the energy demand, for example, changing over time with different scenarios? So from 2015 to 2050 under different scenarios. Okay. The next step is then that we need to know, okay, what is now the optimal configuration? So how do we integrate renewables? We use these optimization techniques where we try to find out what are the optimal combination of systems, heat pumps, photovoltaic, and building envelope solutions. And we do that with a multi-criteria analysis where we optimize for costs and CO2 emissions. And you see then here the Pareto front, basically, of all possible solutions. And Emmanouil will tell you now more about the machine learning-based approach, which is then the next step, basically.
Thank you, Kristina. So, as it was already mentioned, we have an engineering approach at the building level in order to calculate optimal retrofit solutions. But what happens if we go to larger scales, for example, districts or even cities or even at national scale? So ideally, what we would like to do is to apply this engineering approach in every building and derive optimal retrofit solutions for each building, and then process this data and come up with effective energy policies and strategies and give incentives to the people to retrofit their building. However, this is not so easy, and this is mainly due to computational cost. And just to give you an example, if we try to calculate, let's say, the optimal energy systems for around 220 buildings, we might need of up to 42 days with this engineering approach. So our goal is to develop a surrogate model that actually mimics the functionality of this engineering approach and derives near optimal retrofit solutions. Special attention is also given to use easily accessible or already known building data, and also to make this model easily generalizable for other buildings and regions. How do we do that? We start by collecting the necessary building data. We have two case studies. One is the city of Zurich, and the other one is the whole Switzerland, the whole country. For the city of Zurich, we collected data for around 12,800 residential buildings, while for the whole Switzerland case study, we collected data for 100 residential building archetypes, for 53 weather files, so as to have a representative building set for all the different climate conditions of Switzerland. As soon as we have collected the building data, we can apply the engineering approach in order to come up with a set of optimal retrofit solutions. The next step is to actually pre-process this data, and this involves mainly the identification and the remove of outliers, and also the standardization of both continuous and categorical input features. the next step, and maybe the most challenging one, is to actually select the machine learning algorithm to use and also define the structure of this surrogate model. Starting from the structure of the model, we first starting by predicting the CO2 optimal solution. We use input information, as we said, easily accessible building data, like, for example, when this building was constructed and what is the floor area of the building. We also have the Pareto front number as input. So here is 10, one hot encoded. And we also have the heating degree days in order to give some information to the model about the weather conditions. As soon as we have calculated the CO2 optimal solution, we can move on with all the other solutions, predicting all the other solutions with almost the same input data set. However, we have one more input feature, which is the previously calculated optimal solution. So, for example, if we want to calculate the Pareto front solution 9, we need to have as input the Pareto front 10 solution, which is, in this case, the CO2 optimal solution calculated at the previous step. So it's obvious from this graph that we used artificial neural networks, not only because they have been widely and successfully used in the building sector, but also because we can predict simultaneously very well both continuous and categorical data. So after having defined the structure of the model, we move on with the training process. We optimize the model, and then we come up with the best performing surrogate retrofit model, which can be used in a set of test buildings, so as to come up with the optimal retrofit solutions. Before that, though, we have a data post-processing step, which is mainly just a filter to make sure that the outputs of the surrogate model are Pareto dominant points. Let's see how this surrogate performs for the case study of Zurich. On top, we have the CO2 optimal solutions prediction performance, and below we have the all other solutions. The different colors represent the different retrofit dimensions that we want to predict. The blue ones represent the continuous variables, for example, the two objectives value, the cost and the emissions, and the other ones, the energy systems capacity, the storage and the renewables capacity, while the red colors represent the different categorical variables, for example, the system selection and the building envelope intervention. For the continuous one, we use the coefficient of determination as an evaluation metric, and for the categorical one, the F1 score. For both of them, one is the best value. So we can see that for all the Pareto front solutions and for almost all the retrofit dimensions, we have a very good accuracy, which is in most of the cases above 0.85. And in order to give you a better visualization of this prediction performance, we will compare the Pareto fronts calculated from the engineering approach and the surrogate model for a multifamily house built between 1919 and 1948. So in this graph, we can see the Pareto fronts. On the X and Y axis, we have the two objective values. The solid line represents the output of the engineering model, while the dotted one represents the output of the surrogate model. The different marker colors here represent the different building envelope interventions. So in general, we can say that we have a very good accuracy in predicting the objective values with less of 0.25 deviation of the targets. And also we have an almost perfect fit of the building envelope interventions. We can see this graph in another dimension, in the energy systems dimension. So here the marker shapes represent the different energy systems that we select, and the different marker colors represent the different system sizing. Here we can see that we have a perfect matching of the energy system selection. In order to conclude my part, so what we did is that we developed a surrogate model that uses easily accessible building information, so we do not have to explicitly calculate, for example, the embodied emissions and have it as input to our model. We reduced the computational time from 3.5 minutes to 16.4 microseconds without compromising accuracy, as we saw for the case study of Zurich. We are currently working on generalizing those results for the second case study for whole Switzerland. You can see the results in my poster. And now we are currently working to improve this performance by increasing the training data set. And last but not least, I would like to mention that those surrogate models can not only be used to increase the retrofit rate, but also to combine them with engineering models in order to combine the advantages of both worlds.
Okay, we go now to the second example. The situation looks quite different if we now look at developing countries where we have other problems and also other sources of data. So we are looking, a PhD student of us is looking at forecasting the energy demand of rural households to improve actually the electrification planning in developing countries. Why do we do that? So if we look into the numbers, it's 11% of the global population lack access to electricity, and 87% of them live actually in rural areas. There are a number of possibilities how they can be electrified in the future. The worst situation would be if they would be covered with fossil fuels, of course. But there are also others, which is basically a grid connection, or then solar panels, which could be installed either within a microgrid or on their houses. In order to plan that sufficiently, we need to know what is actually the energy demand, and not just for the current situation, but also how will it change if they get electrified. So what appliances do they acquire? So she's developing now an energy demand model for these developing countries with different data sources, which should be applicable to all these developing regions, and then use that also for forecasting how the energy demand will change over time. That's quite a difficult thing to do because actually we lack a lot of data. So it's quite a challenging task. And the process which we identified now, how that could be tackled is, first we need to know, okay, what is the occupant behavior? So how do people behave? What appliances do they actually own, and how does it change if they get electrified? And we produce then current electricity demand and load profiles for now and then also for the future. And we model, we calibrate then this model with measured data. So we use a different machine learning techniques. So one is first the occupant behavior with data mining techniques or agent-based modeling. And then in the second step, actually, when we know how the occupant is behaving, we need to know, okay, what are the appliances, what they actually own. And we use their data, which are publicly available mainly. For example, there are some time of use surveys and also appliance ownership surveys from the World Bank and from USAID. We collaborate a lot with different NGOs and startups to collect data. And she also went actually now to different countries. So, for example, now to Kenya to do field data measurements. I will just show you now one example. So she uses, for example, this random forest technique in order to predict what is the appliance ownership. Here now given for two examples. So first thing, what usually somebody has in a developing country is a mobile phone. And you see here the parameters which are actually influencing how likely it is that you have a mobile phone. So it's basically the age of the household head, household size, and the employment rate. The other one is, for example, a fridge, where you see then how with this collected data, how we can predict that, for example, here for Tanzania, and how accurate our model is. So you see, this is already the better appliances. We got an R-square from 0.7 or 0.6 for these different devices. That can be then mapped in the next step for different countries. So she used now, for example, Nigeria and Ethiopia, and she always used a training data set and then a testing training set. So that's an ongoing study. So she's then the next step then looking how we can actually now predict which appliances will be acquired in the future. So to summarize, useful applications for machine learning in buildings, what we identified is first that clustering techniques are quite good to handle large amount of data sets. For large-scale analysis to improve the time issues and computational costs, whereby we actually target that we do hybrid approaches where we can combine machine learning and these physical-based or engineering models, because they are also quite good in actually predicting the energy consumption and how the system should change in the future. And where definitely machine learning will play a role is if we get more measured data in the future, if we get more smart meter data and so on. There I see a big potential in the future to use machine learning for this data. With that, I'm done. Thank you very much for your attention.
question here.
Thank you very much for the talk. I had a question about the sort of retrofit modeling, and I was wondering if you want to apply your sort of learned models to a very different climate, like Los Angeles with different amounts of sun and air conditioning and all this stuff, do you have to like retrain your model, like collect new data and retrain your models, or do you think it could, with the right feature inputs, it could generalize well to sort of all different climates?
Yeah, so as I had in this slide here, the inputs of our model include one input feature, which is the heating degree days. So we try to provide to the model information about the climate conditions. So ideally, if we get like a good prediction for this model, then you could easily apply to another climate region, for example, in USA or somewhere else. But now we are currently trying to make this model work a bit better. So it works if you don't account like the weather conditions for the case study of Zurich. It works very well. But now we are trying to generalize it for different regions and also different climate conditions.
Other questions?
Thanks. Just a very small question. I think it was 40% of the energy that the buildings were using. How much do you expect to reduce by like optimizing things with this retrofitting?
I think if you look at the numbers at Switzerland, they target something like 2/3 of it shall be reduced. And actually the CO2 emissions should go also quite drastically down. So it's fully decarbonized basically and reduce 2/3 of that energy consumption.
More like a comment. I especially like the idea on looking in developing countries to use actually ML based on relative scarce data sets. I would like to point to Indian household surveys. There's really rich data sets available. They give a lot of information also to actuaries with a few publications out there that could be used, perhaps not to directly use it, but to gauge also like what's going on in a similar context.
Okay, thank you very much. Do you know, is it also World Bank or who is collecting this information?
No, it's, I mean, like there's Indian household surveys, it's really by the Indian government,
Okay.
over like a panel survey with like hundreds of thousands of households. And there are a number of people involved in investigating those, including there's in Oxford going on, they do additional surveys. We are doing also additional surveys in Tidabarat, that's just in one city. So like a lot of activities going on with the detailed household data on energy consumption and demand.
Thank you.
One more question. Are you planning to look into air conditioning?
Yes. So at the moment, I mean, since we have a lot of funding sources from Switzerland, air conditioning is not so much of an issue because households are not, at the moment, not air conditioned. But that with climate change, of course, that will change. And we are looking into how actually that load can be covered in the future. And then maybe also to come back to your point, to your question before, that would be then also actually you have to retrain. If you have additional systems, like air conditioning system, you would have to retrain the model because now at the moment we are not accounting for that.
Let's thank again Kristina and Emmanouil.